Guys, welcome to the first video in the LearnAPChem series here at LearnAP. Before we get started, I want to remind everybody that we do live streams every Sunday from 5 to 6 p.m. Eastern, where we answer your questions about APChem, so be sure to check those out. Also, if you have any questions, please leave a comment. I'm active in the comments, so be sure to ask a question if you have them, and I'll help you out. Alright, well in today's video, we're going to be talking about the atom. In particular, laws of matter, protons, neutrons, and electrons, history of the atom and famous experiments, the Bohr Model, valence electrons, ground state versus excited state, and the Heisenberg uncertainty principle. Although this stuff is pretty basic, much of this stuff is also really fundamental, so unless you're really confident that you know all this stuff, I recommend that you watch this because this material is very important. So without further ado, let's get to it. So let's start by talking about John Dalton's atomic theory, which has three main postulates. The first is that all matter is composed of individual particles called atoms that cannot be created or destroyed, also known as the law of conservation of matter. Alright, so the second rule is that each element has atoms that are identical to each other in all of their properties, and these properties aren't the same as other elements. So all this is saying basically is that if we have two atoms that are the same, let's say we have two oxygens, they're going to be identical in all of their properties. However, if we have, say, a different element, like let's say nitrogen, they might have some common properties, but all of their properties are not going to be the same. And this would go with any other pair of different atoms, so say oxygen and carbon, or maybe lithium and uranium. These are not going to have all the same properties, but two atoms that are the same will have all the same properties. Alright, so the third rule is that chemical reactions are rearrangements of atoms from one combination to another. And all this is saying is, let's say we have a really simple reaction. We're splitting salt, sodium chloride into sodium metal and chlorine gas. All this is saying is that these atoms in this reaction are just being rearranged. And that's sort of tying into this first one, that atoms aren't being created or destroyed. And that leads us to the law of multiple proportions, meaning that atoms combine with each other in whole number proportions. So, for example, everybody knows H2O is water. This could not be written as HO 1/2. Atoms combine in whole numbers, so you would never see a fraction in there. Alright, so let's talk a little bit about the history of the atom. It's important to note that you don't have to memorize these dates or anything, but you should kind of have an idea of the people, what they did, and kind of the order of what was going on. So we're going to start with the oil drop experiment in 1909. Robert Millikan determined the charge of the electron through this experiment. Not going to go into detail about how he did it, but just know Millikan, oil drop experiment, charge of the electron. Alright, so J.J. Thomson, about 10 years earlier, did cathode ray experiments, and this is where he discovered the electron in 1897. He also determined the charge to mass ratio of an electron, and he came up with the plum pudding model in 1904. And this was basically his theory of what an atom looked like. And what it was basically, we have this sort of positive dough type thing. And inside this dough, there are little particles of negatively charged things, which he discovered, the electrons. This was later disproven, and this was by the gold foil experiments. Ernest Rutherford shot alpha particles, which are basically 2 protons and 2 neutrons, at a sheet of gold foil. Most of them pass right through, but some of them bounce backwards. This led to the nuclear model of the atom. Rutherford deduced that these alpha particles, which I'll show right here, just 2 protons, 2 neutrons, were hitting off some sort of tightly packed nucleus, and that's why they were bouncing back. So that's how he came up with the nuclear model of the atom in 1911, saying that atoms are mostly empty space, which explained why most of the alpha particles were going right through, except for a small, tightly packed nucleus, which is why some of these alpha particles were bouncing back the other way. Rutherford also discovered the proton, and then in 1932, James Chadwick discovered the neutron. Alright, so let's talk about the Bohr model now. Niels Bohr in 1913 produced the Bohr model, consisting of a small, tightly packed nucleus surrounded by electron orbitals in a circle. So how would we draw the Bohr model? So first we just want to determine how many protons and neutrons are in the atom. I'll talk about this in a later video, but for right now we're going to start with hydrogen, which is very simple. We just have 1 proton. And then we're going to draw the same amount of electrons on these orbitals. Now hydrogen only has 1, but many other atoms have more, because orbitals can only have a certain amount of electrons. And we can find how many electrons each orbital can take by this simple formula here, 2n squared. So this first orbital at n equals 1 has 2 times 1 squared, 2. If we had n equals 2, 2 times 2 squared, or 8. So if we had, say, 3 electrons, we would draw another electron here, and then we would draw another circle around and put an electron on there. Also note that when you draw these Bohr models, you should try to draw the electrons further away from each other. So don't draw another electron right here. It's not incorrect, but it's just really bad form, and you would almost never see that. It's worth noting that the Bohr model is wrong for every atom except for hydrogen and helium. And I'll talk about why that's the case more in the upcoming video, but for right now, just know that. Alright, so now let's talk about valence electrons. Valence electrons are described as the electrons that surround the last orbital of an atom. Essentially, all we have to do to find valence electrons, if we have a Bohr model, is we look at this outermost orbital and we count the number of electrons. So here for hydrogen, it would simply be 1. If you didn't have a Bohr model, there's an easy way to do it, and again, I'll cover this in a later video. Note that electrons would like to occupy the lowest possible orbital. This is called the ground state. So if we wanted to draw the Bohr model for hydrogen in the ground state, we would draw it like so. But when there's more energy added to an atom, the electrons may move up orbitals, and this is called the excited state. So if I want to draw a little excited state here of hydrogen, we can draw this electron on the second orbital. But note that if you're asked to draw a Bohr model, you should assume ground state unless otherwise specified. Alright, let's talk about the Heisenberg-Uncertainty Principle, which states that the exact position of particles in an atom cannot be determined precisely. So all this means is that, let's say we just have some atom, we'll say hydrogen here because this is pretty basic, we have the Bohr model. I can't determine the precise position of particles inside this atom like this electron right here. I can only describe it in terms of probability. You won't actually have to do any calculations with this principle. You just need to know the concept of it because you might be asked about it on the AP test. Alright, so that brings us to today's challenge problem. Draw the Bohr model for nitrogen, which has 7 protons and 7 neutrons. Also, how many valence electrons does nitrogen have? The solution to this is on our website, LearnAPChem. The direct link is also in the description. If you found this video helpful, please like and be sure to subscribe for future content. Like us on Facebook and follow us on Twitter for updates about our new videos and live streams, which we do every Sunday, where we answer your questions about AP Chem from 5 to 6 p.m. Eastern. Links for that will also be in the description. If you're looking for resources to help you learn AP Chem, be sure to check out our resource recommendation video. The link for that will also be in the description, and you can also click on the screen now to be taken to that video. Alright, well, leave a comment if you're still confused about anything, or also any other comments on the video in general. Other than that, I want to thank you guys for watching, and I'll see you in the next video. Alright, so let's talk about protons, neutrons, and electrons. Atoms themselves are composed of three main particles: protons, neutrons, and electrons. Protons have a charge of +1, electrons have a charge of -1, and neutrons have no charge. So what this means is that one electron is going to cancel with the charge of one proton, while neutrons have no charge. Protons and neutrons have a mass of 1 U, or dA. So U means atomic mass units, and dA stands for Daltons. You might also see this written as AMU. They're both correct. And a Dalton and an AMU are the same thing. So 12 Daltons, or 12 AMUs, is described as the mass of one carbon-12 atom. So you might be wondering, okay, well, what does this mean? Well, carbon-12 has 6 protons and 6 neutrons. So we can say from that 1 U, or dA, is approximately equal to the mass of 1 proton or 1 neutron. It's not exact, but this is a pretty good formula to go off of. Note that electrons weigh far less than protons and neutrons. They do have mass, but when you're working with calculations, it's pretty much negligible, so you don't have to worry about it.